Hey everyone, welcome. Today, we're tackling a Leetcode problem called minimum number of operations to make elements in array distinct. It sounds a bit wordy, but don't worry, we'll break it down together, step by step. Ready? Let's dive in. Okay, so here's the main idea. We're given a list of numbers, called, our goal is to make sure all the numbers left in the list are unique, distinct, no repeats. The only way we can change the list is by chopping off the first three elements. We can do this chopping operation as many times as we need. We want to find the fewest number of chops, or operations, to get to a state where the remaining part of the list has only unique numbers. Oh, and an empty list is always considered unique. Okay, let's trace example 1 from the official image. We start with 1, 2, 3, 4, 2, 3, 3, 5, 7. Are the numbers unique? Nope. We see 2 twice and 3 3 times. So we need at least one operation. Operation 1. Chop off the first 3. 1, 2, 3. We're left with 4, 2, 3, 3, 5, 7. Now, are these numbers unique? Still no, because 3 appears twice. Okay, so one operation wasn't enough. Operation 2. Chop off the next 3 from the current list. 4, 2, 3. Now we're left with 3, 5, 7. Are these unique? Yes. 3, 5, and 7 are all different. Great, we stopped after 2 operations. So, the minimum number of operations is 2. Make sense? Let's try example 2. 4, 5, 6, 4, 4. Clearly not distinct because of the 4s. Operation 1. Remove the first 3. 4, 5, 6. We're left with 4, 4. Still not distinct, right? Both are 4s. Operation 2. We need to remove the first 3, but we only have 2 elements left. 4, 4. The rule says if we have fewer than 3, we just remove all of them. So, we remove 4, 4, and we're left with an empty list. Is an empty list distinct? Yes, the problem says it is. So we stopped after 2 operations. The answer is 2. Okay, so the most straightforward idea, like we just did in the examples, is to just simulate the process. We start with 0 operations. Then we check, is the current list distinct? If yes, we're done, return the count. If not, we perform one operation, chop off the first 3 elements, and add 1 to our operation counter. Then we repeat, check the new, shorter list. Is it distinct? Keep going until the list becomes distinct. To check for distinctness efficiently, we can use something like a hash set. We just add elements to the set as we see them, and if we ever try to add an element that's already in the set, we know we have a duplicate. Now, how fast is this simulation approach? Let's say the original list has items. In the worst case, we might have to do the chopping operation, about n, divided by 3 times. Okay, but each time we check if the remaining list is distinct, that check itself could take time proportional to the length of the remaining list. In the beginning, that's almost n items. So we're doing roughly n/3 checks, and each check might take up to order n time. Multiplying those gives us something like big O of n squared time complexity. That might be okay for small lists, but it could get slow if the list is really long. The space needed is mostly for the hash set we use during the check, which could also be up to order n space in the worst case. Can we maybe do better? Let's flip the problem around. We want the minimum number of operations. Each operation removes 3 elements from the start. So fewer operations means we remove fewer elements from the start. If we remove fewer elements from the start, we are left with a longer piece at the end, right? So minimizing the operations is the same as finding the longest possible ending part, the suffix, of the original array that already has distinct elements. Does that make sense? If we can find the starting point of that longest distinct suffix, we know exactly how many elements came before it, and that tells us how many operations we needed. So how do we find this longest distinct suffix efficiently? We can work backwards. Let's start from the very end of the array. We'll use a hash set again, let's call it scene, to remember the numbers we've encountered in this suffix part we're building. We look at the last number. Is it in scene? Nope, scene is empty. So we add it to scene. Then we look at the second to last number. Is it in scene? If no, great. Add it to scene and keep going left. We continue this process, moving left one step at a time. As soon as we encounter a number that is already in our scene set, bam, we found a duplicate. This means the distinct suffix cannot include this number. It must start immediately after this duplicate's position. If we manage to go all the way back to the beginning of the array without finding any duplicates, it means the entire array was distinct to begin with. Okay, so once we find that first duplicate going backwards, let's say it's at index I, we know the longest distinct suffix starts right after it, at index I plus 1. This means all the elements before index I plus 1, that is, elements from index 0 up to index I, need to be removed. How many elements is that? It's exactly I plus 1 elements. Now remember, each operation removes 3 elements. So, how many operations does it take to remove I plus 1 elements? We need to take the ceiling of I plus 1 divided by 3. A neat trick in integer division for ceiling x to swy 3 is x plus 2 to swice to swime. So substituting x equals I plus 1, we get I plus 1 plus 2 slash 3, which simplifies to just I plus 3 slash 3. If we didn't find any duplicates, our stopping index I is effectively minus 1. Plugging that in, 1 plus 3 plus slash 3 equals 2, slash 3 equals 0. 0 operations, which is correct, for an already distinct array. Alright, here's the Python code for this reverse traversal approach. Don't worry if it looks like a lot at first glance. We'll walk through the key parts. You can see the loop goes backwards, from n1 down to 0. It uses a set called scene. It finds the index of the first duplicate, calculates how many elements need removing, and then figures out the operations using that integer division trick we just talked about.